The question of whether Uranus's moons could support alien life has fascinated scientists and space enthusiasts alike, propelling new research and igniting discussions about the icy, distant moons orbiting this enigmatic planet. With a cold, remote position in our solar system, Uranus may seem an unlikely candidate for life. However, several of its moons exhibit intriguing features that make them worthy of deeper exploration. Here's a journey into the factors that could determine whether life might exist on these frozen, mysterious moons. Uranus, the seventh planet from the Sun, orbits nearly 1.8 billion miles away, lying at the outer edge of our solar system's habitable zone. Unlike its gas giant neighbors, Jupiter and Saturn, Uranus is classified as an ice giant. The planet's composition includes heavier elements and compounds, such as water, ammonia, and methane, which exist in solid or superpressurized forms under the planet's atmospheric layers. Surrounding Uranus are at least 27 known moons, with 5 major ones: Miranda, Ariel, Umbriel, Titania, and Oberon, forming a captivating set of icy celestial bodies. These moons have caught the attention of astrobiologists because of certain characteristics, including possible subsurface oceans, geological activity, and a composition rich in water and organic compounds. While not much is known due to the limited data from Voyager 2's 1986 flyby, the information it captured suggested an active and dynamic environment on some of Uranus's moons. The outermost moons, especially Titania and Oberon, may possess subsurface oceans buried beneath miles of icy crust. Such oceans, potentially warmed by tidal flexing, gravitational forces caused by Uranus and neighboring moons, create a tantalizing prospect for life. Tidal flexing may generate heat as icy layers shift under gravitational pressure, forming fractures and creating enough internal warmth to keep a layer of liquid water between the crust and core. This type of heating mechanism is observed on Saturn's moon Enceladus and Jupiter's moon Europa, both of which are prime candidates for microbial life in our solar system. If a similar process occurs on Uranus's moons, their subsurface oceans could become isolated, stable environments, shielded from the harsh radiation and frigid vacuum of space. In these conditions, extremophiles, organisms that survive extreme environments on Earth, might find a way to adapt and evolve. Another consideration is the chemical composition of Uranus's moons, especially Ariel and Umbriel, where a mixture of ice, carbon dioxide, ammonia, and possibly organic molecules hints at the complex chemistry that life as we know it requires. Ammonia, a compound containing nitrogen, is crucial in forming amino acids, the building blocks of life. If this ammonia were to combine with other available compounds in a subsurface ocean, the potential for organic reactions might arise. Carbon dioxide and methane could serve as energy sources for hypothetical microbes, similar to how organisms around Earth's hydrothermal vents metabolize chemicals like hydrogen sulfide and methane. These processes drive an ecosystem independent of sunlight, thriving on chemical energy, a potential parallel to what might exist on Uranus's moons. One of the most captivating possibilities for life on Uranus's moons involves the potential role of water-rock interactions in generating energy and complex molecules. In these hidden oceans, water could come into contact with rock layers, initiating chemical reactions that produce hydrogen and other compounds usable by hypothetical microorganisms. Hydrothermal vents on Earth's ocean floor operate on this principle, providing energy to entire ecosystems deep in the dark, cold ocean. Similar processes could take place in the icy depths of Uranus's moons, where mineral-rich water might enable the formation of simple molecules like methane. Over time, and with the right conditions, these molecules could theoretically lead to the evolution of life. A key question surrounding Uranus's moons is whether the presumed subsurface oceans could remain stable over long periods. The isolation of these oceans might help protect any potential life forms from radiation and temperature fluctuations, providing a consistent habitat for microbial life to thrive. However, without more substantial geological activity or continuous tidal heating, the water in these oceans could eventually freeze solid, ending any chance of life. The preservation of liquid water is critical, and factors such as Uranus's orbit, its tilt, and the gravitational influence of other moons play into whether these subsurface environments remain stable. For life to exist, these moons need a steady input of energy to counter the freezing cold beyond Uranus's icy surface. Future exploration of Uranus and its moons could transform our understanding of where life might exist in the universe. To date, no spacecraft has returned to the Uranian system since Voyager 2's flyby, making it one of the most underexplored areas of our solar system. A dedicated mission to study Uranus and its moons could examine signs of subsurface oceans, determine whether geological activity is ongoing, and analyze surface compositions to pinpoint potential hotspots for life. Such a mission might deploy advanced technologies to detect biosignatures or organic molecules from afar, perhaps even sampling plumes or vent-like emissions if they exist. As we expand our exploration to the outer solar system, the secrets of Uranus and its icy moons may bring us closer to answering one of humanity's most profound questions: are we alone in the universe? The potential for alien life on Uranus's moons continues to intrigue scientists, who see these icy worlds as vital pieces in the puzzle of life beyond Earth. Despite their great distance from the Sun, several factors suggest that the moons may host unique environments capable of sustaining microbial life. Building on this idea, there are additional aspects and scientific theories that contribute to our understanding of the possibilities for life on these remote, enigmatic moons. First, recent advances in the study of icy bodies in the outer solar system offer promising parallels to Uranus's moons. Investigations of moons like Europa and Enceladus have shown that liquid water can exist beneath thick ice crusts, thanks to gravitational forces that induce internal heating. This discovery suggests that similar processes could be at work on Uranus's moons, where subsurface oceans may be hidden from view. If Uranus's moons have similar icy crusts with liquid water underneath, they could possess the necessary medium for life. On Earth, water acts as a solvent and a medium for biochemical reactions, making it essential for life as we know it. Therefore, if any of Uranus's moons have subsurface water, they might also have environments where primitive, resilient life forms could theoretically develop. Beyond liquid water, an interesting possibility arises in the potential existence of complex organic molecules on Uranus's moons. Carbon-based compounds are essential for life, and scientists believe that chemical processes triggered by solar radiation or cosmic rays could form these compounds in icy environments. This process has been observed in distant celestial bodies like comets, which contain a wealth of organic material. If organic molecules exist on Uranus's moons, particularly in places where subsurface water might interact with mineral-rich rock, they could serve as building blocks for primitive life forms. Such environments could allow for the gradual formation of increasingly complex molecules, possibly even leading to prebiotic chemistry, the first stage in the emergence of life. Moreover, the intriguing phenomenon of cryovolcanism, cold volcanic activity in which water, ammonia, and methane are expelled from the interior, might occur on some of Uranus's moons. Cryovolcanic activity has been observed on Saturn's moon Enceladus, where plumes of water and organic compounds escape through surface cracks and vent into space. If similar plumes exist on Uranus's moons, they might serve as windows into the composition of any subsurface oceans and provide a pathway for analyzing the chemical makeup of these hidden habitats. Sampling plumes, if they exist, could reveal essential compounds that hint at biochemical activity or, at the very least, complex organic chemistry. Another significant factor that could influence the likelihood of life on Uranus's moons is the presence of ammonia and methane. These compounds play a unique role in creating a viable environment for life, particularly by lowering the freezing point of water, thus allowing subsurface oceans to remain liquid at lower temperatures. This property could make the inner conditions on these moons warmer and more stable than initially assumed. Ammonia also participates in essential chemical reactions that might promote the development of organic molecules and, under certain conditions, could support primitive metabolic processes. Additionally, methane could serve as an energy source for certain types of life forms, much like organisms on Earth that metabolize methane in oxygen-poor environments. Lastly, the exploration of Uranus and its moons has become a higher priority for space agencies, which are eager to investigate these icy bodies for signs of habitability. New mission proposals aim to send advanced instruments to analyze surface compositions, map potential cryovolcanic regions, and detect any plumes or geysers. Such missions could utilize radar and infrared spectroscopy to penetrate ice crusts and assess the chemical composition of the surface. Potential landers or probes might explore Uranus's moons up close, directly sampling ice layers and searching for biosignatures, organic molecules, and isotopic ratios indicative of life. If such a mission finds promising results, It could open up the door to further exploration, eventually leading to the development of life-detecting equipment specialized for the icy terrains of Uranus's moons. The journey to understand whether Uranus's moons could harbor alien life is only beginning, and the evidence so far suggests there are many more secrets waiting to be uncovered in these icy worlds. While definitive proof of life on Uranus's moons remains out of reach, the combination of potentially stable environments, presence of organic molecules, and complex chemistry makes them one of the most exciting prospects in the search for extraterrestrial life in our solar system.